Welcome, ladies and gentlemen, to our lecture on potential energy and conservation of energy. So, generally, we define energy as the capacity to do work. And remember, we talked about work in our last lecture. And so far, we've only talked about kinetic energy. So it seems like energy is always changing, right? We give an object kinetic energy when we give it some velocity. And that kinetic energy is 1/2 mv squared. So it seems like we're adding energy to and removing energy from the universe as we do work on objects, right? As we give objects different kinetic energies. But let me spoil the ending here a little bit, and I want to do this at the beginning and return to it at the end, because this is the single most important point of this section of class material. Energy is a conserved quantity of the universe. So what do we mean by conserved? It means that energy is never created or destroyed. We always have the same total amount of energy in the universe, and we have mechanisms that move the energy around. We have energy changing forms to different types of energy, but we are never creating or destroying energy itself. This rule has no exceptions. When we account for everything in a system, energy is always conserved. So let's go forward and look at how we have energy changing forms. So we learned about kinetic energy, and we learned that this is the energy of motion. But if energy only ever changes types, there must be other kinds of energy. And the other kind of energy that we'll be most concerned with in this class is potential energy. This is energy that an object has because of its state, okay? In particular for us, because of an object's position. So for right now, we'll be concerned with two kinds of what we'll call potential energy, okay? Two kinds of energy that come from the position of an object. We have gravitational potential energy, and we have elastic potential energy. Gravitational potential energy is a representation of the work that gravity could do to an object when we raise it to a certain height. So let's think about a simple system that we've thought about many times, okay? Let's think of somebody dropping off of a high dive. They drop down into the water below here, and they drop some height, h. If we think about the work that gravity does in this system, if we pick, say, x hat, we know that our work is going to be equal to the force of gravity dot, let's use h for this problem, the displacement, right? So we have the dot product of the displacement and the force of gravity, and this is going to be the work that gravity does on the person. Well, the force of gravity when this person is in free fall is mg, and the displacement here we've marked as h, and then they're pointed in the same direction, right? This is vertical displacement and gravity is vertical. They're pointed in the exact same direction, so we don't have any cosine here, right? We have cosine of 0, which is 1. This work that gravity would do to something that falls from this height is gravitational potential energy, okay? So anytime something is some height above another point, it has that much gravitational potential energy when compared to that point, okay? So this is always related to a change in an object's height. All right, so if we have potential energy and we're comparing to this point, then this new distance d, this is going to be mg d. Or another way to look at this, right, is if instead of looking at some shorter fall and saying that that's some other potential energy, if I pick 0 anywhere along this line on h, this distance, this change in height that the person goes through, will still always be the same. It doesn't matter where I pick 0. once I add up the positive and the negative pieces, it's still going to add up to this same change, h. So the physics doesn't care how we do the math. The result, the energy, the kinetic energy that we add as we convert gravitational potential energy to kinetic energy is going to be the same based on the change in the object's height over whatever event that we're considering. Okay? In this case, the event is the person falling from the top of the high dive to the water. So we know that if we have some object and we release it and it falls some height h, we know that we convert this gravitational potential energy, mgh, into kinetic energy, okay? And you know that intuitively. If I raise an object up and I let it go, we see that it has this gravitational potential energy based on its height, and then as that height decreases, this gravitational potential energy goes down, but as it's going down, the speed of the object goes up, and its kinetic energy goes up, right? We convert that gravitational potential energy into kinetic energy. But then once it's on the ground, I can always change its potential energy again by picking it up, can't I? I can raise it back up, h. Okay? And then I'm adding to the gravitational potential energy by giving it energy from my body, from my muscles. Okay? The other main kind of potential energy that we'll be concerned with is elastic potential energy. And remember, an elastic object is one that will return to its original shape after some small deformation. Our classic example of this is the spring that we've talked about before, right? So we have some spring. We have it squished by some distance x from its equilibrium point. So this is where this point over here is where the spring would sit if there was nothing interacting with it. Now for the spring, we can also calculate the work done. But in this case, the force is always changing, right? Because we know that Hooke's law says that the force of the spring is minus kx, okay? So then, to calculate this one, we have to do an integral. And we would have to do an integral from minus x to 0. And then the force, we'd have force of the spring dot dx. We're going to integrate over the distance, right? And then this fs dot dx, well, they point in the same direction, x hat, right? And so what this ends up being is we put our minus kx in here, and then we integrate. And if we integrate, we'll see that what we come up with is 1/2 k x squared. This is our elastic potential energy. It's the work that we must do on a spring to deform it, or the work that it's capable of doing as it returns to its equilibrium position. Okay? Just like gravity, this gravitational potential energy was the work that gravity could do in causing an object to fall, or the work that we would have to do to give the object this potential energy, right? The amount of work that we have to do to raise something up a certain height. This elastic potential energy is the same. It's the work that we have to do to deform this spring by some amount x, or it's the amount of work that the spring can do when it returns to its equilibrium position from some distance x. This gives us a new way to look at things like springs, where force is always changing, and it gives us a way to solve for quantities in these systems very simply. Notice that the two kinds of potential energy that I've given you don't cover all of the different forces that we considered when we were looking at systems using Newton's laws. In particular, these two types aren't covering something like the force of a push, right? Or like the force of friction. The force of a push comes from a chemical reaction in your muscles. This converts what we call chemical energy, or energy stored in the molecular bonds of a material, into the mechanical energy of your body moving. The force of friction takes a mechanical process, these two surfaces sliding past each other, and converts that energy into heat. Chemical energy and heat are two forms of internal energy. And internal energy is just what it sounds like it is. It's energy that's internal to an object. The hallmark of internal energy is that it's not reversible. So what do we mean by reversible? If we take the example of gravity, we said that when we release an object, it readily gives its potential energy back as kinetic energy, right? And then we said, if we want to get that potential energy back, all we have to do is run that falling motion in reverse. We just have to take the object and raise it back up to that same height. Okay? For something like friction, if I push this block along the ground in this direction, then friction just works against me, right? And it creates heat. And if I travel some distance this way, I get some set amount of work that friction does. It converts a certain amount of energy into heat. But then if I run the process in reverse, okay, if I push it back this way, I just get the opposite, right? Now when I push it this way, the force of friction pushes against me, okay? So in both cases, the force of friction just pushes against me and produces more and more heat, right? You can do this by putting your hands together and rubbing them against each other really fast, right? You don't add heat in one direction and remove it in the other. You just add heat with each time you rub your hands back and forth, and both directions produce the same amount of heat. So when friction does work on an object and I get this internal energy of the object, I can't just do negative friction and get the energy back, okay? We call a process like this that isn't readily undoable irreversible. And irreversible processes change the internal energy of an object. What this means is that we don't have a nice formula for friction energy like we do for something like gravitational potential energy or kinetic energy, but we can always still calculate the work done by friction. So we could always calculate the work. We call forces like friction that cause changes in internal energy non-conservative forces. But this just means that they aren't conserving what we call mechanical energy, which is potential energy and kinetic energy. What this doesn't mean is that these forces don't conserve energy, okay? They don't conserve what we call mechanical energy, but they do conserve total energy. When I drag something along and friction acts on it, the energy that heats the object is equal to the work that friction does on the object. Energy is conserved in the process of changing an object's internal energy, but because the process is not readily reversible, it acts as though mechanical energy is lost. But I want to be completely clear here. The total energy in the universe is always conserved. It always stays the same. So if we can calculate how much work friction does as we push an object along on the ground, we can also calculate exactly how much it is heated because we'll know exactly how much energy went into heating the object. So this brings us our shiny new physics tool, conservation of mechanical energy. For this, we start with the universal law of conservation of energy. And this one is really simple to state. EI equals EF. That's it, okay? So if we have some process that occurs, the total energy at the beginning of that process or the beginning of that event is equal to the total energy at the end of that process, okay? This one is true, period. This is an immutable law of the universe. So then, how do we write this for mechanical energy? How do we make this useful for solving the kinds of problems that we're going to be interested in this class? So we start with potential energy and kinetic energy. If there are only forces associated with potential energy involved, then our conservation of mechanical energy formula looks like this. We have some potential energy at the beginning of the event. We have some kinetic energy at the beginning of the event, and that's equal to the potential energy at the end of the event plus the kinetic energy at the end of the event. Okay? You can see that all I did is say that my total energy is potential and kinetic both before and after the event. Okay? It's really that simple. We just say our potential plus kinetic energy at the beginning of an event is equal to our potential plus kinetic energy at the end of an event. And now all I have to do is be able to write the formulas for the potential and kinetic energy of the object at the beginning and the end of the time period of interest. Okay? But this isn't general, right? We know that we may have non-conservative forces acting on our object, like a push or friction. So then we add that to our equation. Okay? We add non-conservative work. So we have potential energy plus kinetic energy at the beginning plus non-conservative work equals potential energy at the end plus kinetic energy at the end. Okay? Now, all I'm really saying here is that on a lot of occasions, this work non-conservative is going to be negative, right? If it's something like friction, then WNC will be negative, or WNC is less than 0. Okay? So we're subtracting some amount of work, which is exactly what these things do, right? Friction sucks energy out of the system and turns it into heat, okay? It sucks mechanical energy out and turns it into heat. And all our equation says is that we have some total mechanical energy at the beginning, right? We take out or add in work from non-conservative sources like pushing or friction. And then those two things added together will tell us how much energy is at the end of our event. Okay? And we said these non-conservative forces, they don't change the energy in the universe, but they do change the mechanical energy of the system that we're considering. Okay? So this is an important piece of our equation. So our general conservation of mechanical energy equation looks like this. And this is the same as saying E initial equals E final. Okay? That's all we're getting down to. This is just conservation of energy. So to use this tool, I have to write the formulas that pertain to the different energies in my problem. I have to identify the potential energies, write the formula for them, identify the kinetic energy, write the formula for it, and identify any non-conservative forces and figure out the work that those forces do. Okay? Then for the final state, I just have to identify any potential energies that are at the final state and any kinetic energy that's in the final state. And then once I fill in each of those pieces, I'm really just down to doing some algebra to solve for the thing that I care about. So if I want to find V final, it's going to come in right here, right? Because this is going to be 1/2 mVF squared, because 1/2 mv squared is kinetic energy. And if I'm looking for V final, then I'll have some stuff for the rest of these, and I'll just do algebra and see what V final is. Okay? This proves to be an exceptionally powerful tool for considering physical systems and solving for quantities that we would like to know. So let's look at a simple example here. Let's solve for a block on a frictionless ramp. Let's say we have a block here, and we're going to look at the speed when it's here at the end of the ramp, okay? This ramp has some distance x, has an angle theta here, and it has a height y, okay? The block is sitting at the top of some height y. So in the past, we looked at blocks sliding down frictionless ramps, and we used Newton's second law and kinematics. And if I asked you to find the velocity of the block at the bottom of the ramp of height y, So say you're not given x. I just gave you y and asked you to find the velocity of the block at the bottom of the ramp. You would choose a coordinate system. You would use Newton's second law to find the acceleration of the block. You'd use kinematics to solve for the speed, and you'd use trigonometry to find whatever the length of the ramp is, okay? So I would look at this thing and I would say, okay, there's mg pulling down on it, and there's n going out normal to the ramp. And in frictionless, I would say, well, I'm not really concerned with n and with the component of gravity that points normal to the ramp. What I'm really concerned with is what's going down the ramp. So I would say, in the x direction, as I've drawn it, I would have mg sine theta equals ma. And that would tell me a equals g sine theta. Okay? And then I would use kinematics and say x equals 1/2 a t squared, which tells me that t equals 2x over a. I would say v final equals at equals a 2x over a in a root equals 2xa all in a root. And then I would replace the a, because that's actually g sine theta, right? But I don't actually know x, so that one's not useful to me. But remember, if my ramp looks like this, like it does in the picture up here, and this is x, and this is y, remember SOHCAHTOA tells me that sine theta, so, is opposite over hypotenuse. So opposite y over hypotenuse. And that tells me that x sine theta equals y. And that's in my equation over here, right? I have x and I have sine theta. So then VF equals 2gy in a root. So it was solvable, just knowing the height of the ramp, but I did need the ramp to make a right triangle, right? I needed it to be a straight ramp, not a curved ramp. And it took some doing, right? I had to use Newton's second law, I had to use kinematics, and I had to use some trig to get it down to the variables that I care about, okay? To simplify it to the variables that I actually know. But now let's solve this with mechanical energy. If we solve this with conservation of mechanical energy, we start with this equation here. And then I say, okay, what's initial and what's final? Well, initial is the block sitting at the top of the ramp, okay? Final is the block down at the bottom of the ramp with some velocity, v. So initially, I have this side over here, okay? First, do I have potential energies? I do. I have gravitational potential energy, right? And that's mg y, okay? Now in this, I do have to choose a coordinate system, although when we use conservation of energy, we oftentimes don't write our coordinate system, but in this case, I've just chosen 0 to be at the ground, okay? And then y hat, x hat. And so when I start, I'm just some height above the ground, and that height is y, okay? So I have mgy, that's my gravitational potential energy. When I start, I'm at rest. So my kinetic energy is 0 because 1/2 mv squared is always the kinetic energy. And when I'm at rest, this v is 0. So my kinetic energy is 0. Then I look at my non-conservative work. So do I have any non-conservative forces in this problem? This problem is frictionless. We're not considering any kind of friction or air drag or anything like that. So we're saying that gravity just pulls it down the ramp. So we don't have any non-conservative forces. We don't have any non-conservative work done. So we've looked at each term in the initial side. Then we look at the final side. On the final side, do I have any potential energy anymore? I set my coordinate system so that 0 was at the bottom of the ramp. So now when we're at the bottom of the ramp, we don't have any potential energy anymore, right? Our height, remember gravitational potential energy is mgh, our height is 0. So this term is 0. And then at the end, do I have kinetic energy? Well, at the bottom, the block is moving. So yes, I do have kinetic energy. In particular, the thing that I was asked to find is how fast the block is moving. Okay? So here it is. And then if I just multiply the whole equation by 2, I get rid of this 1/2 and bring a 2 to this other side. If I divide the whole equation by m, the m's cancel, and I have 2gy on this side. And then, of course, the VF is squared, so I'm going to want to take a square root of the whole equation. And there it is. Solving this problem is a little two-liner with conservation of energy. And ooh, baby, do we like that. But we can go a step further than that, even. What if the ramp was curved? So what if the ramp instead looked like this, with this same height y? In the past, with your tools of Newton's laws and kinematics, you kind of just had to throw up your hands and say, we don't know what the speed at the bottom is. The forces are always changing. The acceleration is always changing. I can't tell you what the speed at the bottom is, okay? I couldn't solve it because my tools before were for dealing with constant accelerations. But this tool, it doesn't require constant accelerations, right? With this tool, we can solve it. And in fact, in this tool, it's the same exact problem, right? At the top of the ramp, we have mgy. We don't have kinetic energy if we start from rest. This is frictionless, so we have no non-conservative forces. And at the bottom of the ramp, our potential energy is 0 again, and we have kinetic energy again. It's the same exact problem with the same exact answer. And this is a notable finding for our gravitational potential energy. Without friction, it doesn't matter what the shape of the ramp is, or even if we drop something in free fall. If its height changes by some amount y, then we find the speed in this same way. The difference between falling and frictionlessly sliding down a ramp is not your speed at the bottom. It's the direction of your velocity at the bottom. Okay? If you're falling, your velocity is pointed right at the ground. And when you reach the ground's going to suddenly stop your motion with some unfortunate side effects. But if I go down a curved ramp like this, my speed is directed along the ground at the bottom. And then I can just coast away with all of that speed. But in both cases, my kinetic energy is the same, and thus my speed is the same, because you're converting the same amount of gravitational potential energy into kinetic energy. Could we have understood that from our problem on this side of the dashed line? If we simplified our answer, then yes, we could understand that from this. We can see that the angle doesn't matter in here, right? But we couldn't talk about the shape of the ramp. We could only talk about the angle of the ramp. We could say that the angle is not important. If we descend some height y, we'll have the same speed at the bottom, okay? Energy gave us the tools to talk about this in a much more general way and to realize that all methods of falling some distance y give us the same speed, okay? Now, we know that, say if I was on a skateboard and I could approximate frictionless sliding down this ramp on the right here, I'd have a speed that's equal to my free fall. But don't I change my gravitational potential energy by the same amount if I walk down the ramp? And if I just walk down the ramp, won't I be going a lot slower at the bottom? I will. But if you think about that, when I went through this process at the top, I would have a potential energy at the top if I was going to walk down the ramp. And if I started from a standstill, I wouldn't have any kinetic energy. But as I walk down the ramp, I'm going to push against the ramp, right? And that push, the force of me pushing against the ramp, that does non-conservative work, okay? My muscles are slowing me down. And the static friction of my shoes is sticking me to the ramp. That's what's making my speed different when I get to the bottom, okay? I decrease my gravitational potential energy by the same amount, but I'm not allowing it to be all converted into kinetic energy, right? I'm pushing on the ramp and changing some of it into spent chemical energy. So my speed wouldn't be the same as if I was in free fall from the height y, but it's because I'm doing non-conservative work the whole way down the ramp. If I go to the frictionless example, and I don't do any non-conservative work as I go down the ramp, then my speed is the same no matter how I get to the ramp. It doesn't matter if I drop down, if I jump off the back. It doesn't matter if I slide down the front. And it wouldn't matter if the ramp was shaped like this, with a loop-de-loop in it, but this height was still y. When I get down to the bottom, I will have the same speed if I don't have non-conservative forces pulling energy out of the system. That is to say, if I convert all of my gravitational potential energy into kinetic energy. So I want to end by mentioning a couple more things about potential energy. The first is that the force associated with a potential energy can be found by taking the derivative of the potential energy with respect to the displacement variable. Okay? So F equals minus del U. This is written this way to be general. Okay? It's true in any coordinate system, and this del operator can work in Cartesian or spherical or cylindrical or whatever coordinates. Okay? So, for example, in Cartesian coordinates, F equals minus del U is F equals minus, and then the partial derivative of F with respect to x hat, plus partial F, partial y hat, plus partial F, partial z hat. Okay? Now, your book has a nice derivation of this, so in the interest of time, I'm going to ask you to just read that derivation for kind of further information and further understanding on this. But I wanted to mention this, that F equals minus del U, and I want you to read this part in your book to get the full derivation of this relationship. Okay? And then the last thing I want to mention is energy diagrams. So we have on the x-axis here the displacement, okay, or the position. And we have on the y-axis here the potential energy, okay? So if we look at the example of a spring's potential energy looks like this. It's a horrible drawing. It's a parabola centered at 0, okay? But we get the gist of it from this drawing. So if I pull in one direction or the other, I get a force that pushes back toward the middle, right? I get this potential energy. So if I displace it to this point here, then I have this much potential energy, okay? And you can see that on this thing, I have a negative slope on this side, right? So this del U is going to be some negative number, minus. And then we have a minus, so F is plus. So the force is going to push back this way. And indeed, we know that that's how a spring works, right? If I had a spring in here, and it was squished by this distance, we know that the force would push it back to the equilibrium, right? Likewise, if I displace it to here, I have this much potential energy. And we have a positive slope here. And so F equals minus, and then this del U is positive because we have a positive slope. And so F equals minus in this case. So the force pushes in the minus x hat direction, okay? Back toward the center again. And indeed, if I have this spring here again, and it's normally this long, and then we stretch it to be this long, we know that the force will pull it back this way. So if I give an object some total amount of mechanical energy, E, then at any point in here, the object can sit anywhere along this area, right? And at any point, it'll always have potential energy up to our curve and kinetic energy from the curve to E, okay? Now, the most potential energy that it can have is all of the total energy, which would be right here. And at that point, the kinetic energy will be zero, right? Because all of the energy is potential energy. The same would be true here. All of the energy is potential energy, so the kinetic energy is zero. The maximum kinetic energy that the object can have will be all of the total energy, which occurs right here at the bottom, okay? Where the slope of this curve is zero, a local minimum. This means the potential energy is zero, and it's all kinetic energy, okay? The effect of adding in non-conservative work, like from friction, would just be to change the height of this line, okay? So we would just be moving this line downward. You could think about this as if our cup here of potential energy had a hole in the bottom, and this water was just draining out, okay? And the level just changes. So when we take derivatives of this, we see that we have a non-zero force everywhere but exactly at the bottom, okay? This point exactly at the bottom, because del U will be zero, right? A local minimum has a derivative of zero. That means that the force will be zero, okay? And indeed, this is true. This is like for our spring when it's sitting and it's not stretched or compressed by any amount, okay? This point where there's zero force, we call the equilibrium point. And in our example here, we showed that the force will push back toward the center from either side of the equilibrium point, okay? This kind of potential creates what we call a restorative force, a force that always pushes things toward the equilibrium point, okay? An equilibrium point at the center of a restoring force is what we call a stable equilibrium. And in a plot of potential energy as a function of position, this always looks like a valley, okay? It always has this kind of valley shape. Now, it doesn't have to be perfectly symmetrical. It doesn't have to be whatever this monster that I drew is. It doesn't have to be a perfect parabola. It can have lots of different shapes, but a valley like this, a local minimum in the potential, is always going to be a stable equilibrium. So a really nice example of this is a marble in the bottom of a nice round bowl. You can imagine if we have this nice round bowl, and we have a marble in the bottom, if we displace the marble by some amount up here, there's always going to be a force that pushes it back to the center, right? And if we displace it up here, there's always a force that pushes it back to the center. The marble always rolls back down to the middle of the bowl, okay? This is a stable equilibrium point. And an object in a stable equilibrium will stay there unless we give it enough energy to escape the valley in the potential, okay? So if we raise this energy bar up enough that it can get over the side here, then it can escape a stable equilibrium area, okay? So now let's consider a potential that looks like this, okay? Just some random, weird general potential. In this one, you can see that I have two stable equilibrium points, right? Down here at the bottom of these two little valleys. But I also have this hill in the middle. And right up here at the top, where there's a local maximum in the potential, I'll have zero force on the object, right? This local maximum will also have a derivative that's equal to zero, which means there's no force on this point, which means it's also an equilibrium point, okay? But you can see in this one, this slope on the left over here has a positive slope, which means that the force will be negative. And this force on this potential on the right has a negative slope, which means that the force will be positive. So now, if I displace my object from this equilibrium point, the forces will always push the object away from the equilibrium point. Okay? We call this an unstable equilibrium. And a good example of this would be a ball on the top of a nice round hill. Okay? You can imagine if I put a ball on top of a nice round hill, I could balance the ball up there. There's no net force if I get it right on top and balance it just perfectly. But if I push the ball away from the equilibrium point in either direction, right? If I displace it a little bit and then set it down, the force will always push the ball away from the top of the hill. Okay? So this equilibrium point acts differently than our stable equilibrium point. We can also see that if I had an object down here in this potential, and I gave the object some total energy E, like this, my object would be trapped in this potential, right? When it gets to here, it has all potential energy, no kinetic energy, so it can't keep going in this direction, right? It has no more kinetic energy. And the same would be true here. So my object can oscillate back and forth down here in this little valley, but it can't leave the valley, right? But if I raised the energy up to here, then you can see my object could potentially make it over the hill and down into this other valley. And if, when it went into this other valley, I lowered the energy back down to here, now it would be stuck in this valley, right? It could move around to these points, okay? So if we think of the hill with the valley on either side, we can think of it in physical terms. A nice thing about a plot like this is this plot isn't representing actual hills and valleys, right? It's representing the value of a potential. When we were using it with the spring, it wasn't actually a bowl. But the nice thing is, because the way gravity works, when we look at this, we can think of gravity, and a physical system where gravity has a potential like this is actually going to look like this. So I can think of a hill with a valley on either side, and if I had a soccer ball down in here, and I was kicking it up the hill, I could kick it up the hill and it would roll back to me, right? What is that arrow? And it would roll back down the hill to me, okay? But if I kicked it with enough kinetic energy, if I kicked it hard enough, I would give it enough kinetic energy to make it over the hill, right? And then it could fall down into this stable equilibrium over here. And then if you were on this side and you were kicking the soccer ball, if you're giving it kinetic energy, you could kick it up the hill and it would roll back to you, right? But again, if you kicked it hard enough, if you gave it enough kinetic energy, you could kick it back over the hill back to me. So unless I give it enough kinetic energy to escape this well, we call these valleys in potential energy wells, okay? So in our example with the soccer ball, you're in a gravity well in the bottom of the valley, okay? If I give something enough kinetic energy to escape this well, then it's free to move about within the potential outside of that well, okay? Whatever that looks like. But if I don't give it enough potential energy to escape the well, then the forces on the object around this stable equilibrium point will always push it back toward the equilibrium point, okay? So let's stop there with our consideration of potential energy and conservation of mechanical energy. Our new tool, conservation of energy, is a powerful tool to use in solving new physics problems, and we've also seen already that it can greatly simplify some of the problems that we've considered in the past. As we go forward, we'll do problems that will further illustrate the usefulness of this new tool.